Okay, so today I'm going to go over how to calculate VAB. The short answer of it, well, first of all, let's label A and B. So the short answer here is that the answer is going to be 0. And this is clear to see because these are two open circuits. So open circuit over here and open circuit over here, which means that their voltages are going to be exactly the same as the node that precedes them. So that's clear to me because I have a lot of experience doing these circuits, but to kind of explain why that's the case, let's actually break it down. So there's two different ways that you can think about this. One is the way that I think about, and that's method number 2. And method number 1 is a more logical one that you might find helpful. Okay, so method number 1 relies on understanding of circuits. So let's say, for example, you have a circuit like this. So a really simple circuit, 10 volt source, and let's say 10 ohm resistor, and you have electricity that's going through it like this. Well, the question is, why is there electricity even moving through this? Well, the answer is because there's a voltage difference. So the positive terminal, which is this big one over here, has a voltage of 10 volts, and the negative terminal of the battery has a voltage of 0 volts. So there's a voltage difference that allows the electrons to move. It actually pushes the electrons through the circuit like this, right? So if you didn't have this voltage source, what would happen? Well, oops, let me fix that. So what would happen? Well, I'd like to imagine that the electrons are kind of like people. So let's say we had the circuit and we had a bunch of Smurfs maybe, or here we go. So they're all, along the circuit like this, and they are only as close to each other as their electrical field allows, because remember, electrons are negative, so they like to repel each other. So if they could, they would be infinitely far away from each other, but because they have neighbors, they're kind of squeezed together like this. So this electron can't move any further this way or any further that way because its neighbors are squeezing it together. And that's true for all the electrons because they're in a circle, right? So they're all kind of squeezed together. So they're not going to move. It's like, if you have a subway car and you have a bunch of people that are all like right next to each other, they're all crammed together. They're not going to move one way or the other. But what happens is when you add a battery, the way I like to think about it is the battery is like a little compartment like this. So you have a little compartment and it's empty. And so an electron might go inside like this. So it just curiously walks inside. Not really curiously because it's trying to get away from its neighboring electron, right? So it gets pushed inside by its neighboring electron. And when it gets inside there, there's a little treadmill. That's the electromagnetic force that pushes it and accelerates it out of this little house. So it gets shot out. Well, actually it's purple, so let's keep it purple. So it was in here, and the treadmill is super fast, and it pushes it out, and it smacks its neighbor, and this neighbor goes flying and smacks this neighbor. So if I draw that neighbor goes flying, smacks this neighbor, that neighbor goes flying, smacks that neighbor, and it just kind of goes along like that. So the wave of hitting each other continues until this electron gets pushed into here, and the process continues. So this electron over here moves here, this electron here moves here, and you can imagine that it's like a treadmill on its own. So it's basically whatever electron was here gets moved along, whatever electron was here gets moved along, like this. And it just keeps on going until the treadmill inside this battery dies, right? The battery dies. So, okay. So that's what's going on with a regular circuit. Now, what happens if you have a treadmill, like you have that same situation? So you have a little house with a treadmill that throws the electrons forward, and you have a break in your circuit, like this. Well, what happens is this electron over here is going to get pushed into the neighboring electron, and it's going to be the same as last time. I'm just going to draw fewer electrons to make this drawing a little bit easier. So this electron gets pushed into this neighbor, and that neighbor pushes this guy, and that guy pushes that guy, and that guy pushes that guy, and this guy pushes this guy. But now this electron doesn't really have anywhere to go, right? There's nowhere for it to go. If the voltage is really, really high, like let's say it's 1,000 volts, right? Or 10,000 volts, then what can happen is this can get pushed so hard that it can come over here. And that's what happens with a taser, right? When you have a taser, you have two terminals like that, and the voltage is like 20,000 volts. And the electrons can actually jump from one side to the other because they're pushed so hard. But in this case, in this class, we're not going to imagine, voltages that high, because we're not trying to design devices that could hurt people. So let's just keep it at 5 volts. So 5 volts is enough to kind of push this guy, but he doesn't have anywhere to go. It's like when you're in the subway and you're getting pushed against the window, right? It's like, where do you want me to go? Like, the only thing I can do is like push back. And what you end up getting is this huge collection of humans that are just squished together like sardines, right? So this guy, he has all this force on him to move, but he has nowhere to go, right? So if he has nowhere to go, well, he's just going to stay there, and the current is going to stop. The current is the flow of electrons, right? There's going to be no flow. So eventually the treadmill is not going to have anybody on it. And well, it might still have this electron on it being pushed forward, but there's nowhere for the electrons to go. So there's no current. Okay, if there's no current, let's imagine that there's a resistor over here. If there's no current, then there's no electrons flowing through this resistor. And we know that the voltage drop across a resistor is equal to the current multiplied by the resistance. So the voltage drop is going to equal, well, 0 current times any resistance. The voltage drop is going to be equal to 0. So there's no voltage drop across this resistor. And that's kind of what's, so like for example, if there's 5 volts over here in this battery, there's going to be no voltage drop here. And so the voltage here is also going to be 5 volts because there was no voltage drop, right? So the voltage continues to be 5 volts, and that's exactly true. The pressure on this electron is still 5 volts. You can think about voltage as like pressure. How much pressure are you putting into the circuit to make the electrons move, right? So if you have like a really powerful battery, 500 volts, right? You can get a lot of pressure pushing the electrons through this resistor, which might be a really strong resistor. But if you have a really weak voltage, then let's say you only have like 5 volts, then you're not going to have much pressure pushing through this resistor. And so the current is going to be small, right? The flow of electrons is going to be slow because there's not a lot of pressure. So to go back to this example, the pressure on this electron over here is exactly the same as the pressure released by the battery. So it's going to be 5 volts, right? So in this case over here, an electron might travel down this wire and then in through here, or it could go through here, and there's going to be a certain voltage here. So the electrons here are going to have a certain voltage. Whatever that voltage is, it doesn't really matter. And you know, I extended this a little bit because they're not going to have any voltage drop across an open wire, right? So let's say, for example, the voltage is like 5 volts when they get here. They're going to have 5 volts of pressure or energy when they get here as well, right? You know, this electron is going to push. This electron that's incoming is going to push this electron with 5 volts, and this electron is going to push its neighbor with 5 volts, and they're going to try to push, but there's nowhere for the electrons to go. So what that means is the pressure on this electron at the end being pushed against a subway window is exactly 5 volts because it was 5 volts over here. All right, so this is just an example. I don't know that the voltage at this point here is 5 volts. Sorry, let me just erase this stuff. This could take a second. I don't know why Paint is such a slow software. Maybe because it's free and not optimized. But it's gonna take a second here because it's gonna keep on deleting stuff. Okay, here we go. So whatever the voltage is here is going to be the exact same voltage as over here because there's nowhere for the electrons to go. And so they just push on this electron, and this poor electron over here just has a lot of pressure on him, 5 volts of pressure to be exact, because the pressure over here is 5 volts. Okay, so that's one way to think about it. So over here would be the same situation with B. The electrons are coming down, whatever the voltage is at this area here. Whatever the voltage is here is going to be the exact same voltage as over here. That's because these points are connected simply through a wire, which means that there's no voltage drop between these 2 points. And so that means the voltage is going to be exactly the same between these 2 points. So any voltage that's here is going to be the same voltage as here. So that's 5 volts. And these electrons are pushing the electron at the end, and this poor electron doesn't have anywhere to go, so it still has that 5 volts of pressure applied on him. So the voltage here at B is 5 volts, the pressure here at A is 5 volts. That means that the voltage difference, AB, is 0, because the difference between them is nothing. They're both at 5 volts. So that's one way to think about it. Just to kind of clarify this a little bit more. Just to clarify this a little bit more, if this point A had like some way to get to the negative terminal of the battery, then there would be some flow here, right? And then the voltage here would be different, but it doesn't. So the voltage at this point A is exactly the same as the voltage here. Okay, so that's the way you could think about it, but the way that I like to think about it, which is absolutely incorrect, but it gives you the right intuition for doing these kind of problems, is I like to imagine the electrons like hot water. So the electrons are hot water coming down, and the resistors are like ice cubes, which cool down the water. So the water becomes colder as you move down. Okay, so let's imagine that, let's imagine that we have a circuit that looks like this. So we have a circuit that looks like this. Okay, if I visualize in my head, there's hot water coming out of the battery over here. They go over this ice cube of a resistor right here, and it becomes a little bit cooler, so it becomes orange water. And then it goes through another ice cube, and that becomes cool water, which flows back into the negative terminal of the battery, like so. Okay, now what would happen if we had this kind of situation? If we had a resistor like this, well, if you had hot water coming out of the battery like this, that hot water would flow into this area over here. Oops, sorry, let's go back. So that hot water would flow over the ice cube over here, and it would turn into slightly cooler water, which we'll represent with this orange. And that orange water is going to pool here, right? Whatever the temperature was over here before, let's say the temperature was just, room temperature, this incoming warm water is going to warm it up to whatever temperature it was, like this. And then we're going to go through another ice cube over here, and then we're going to have should be colder than that. So let's say that's going to be this kind of baby blue kind of light color. So you can see that there's hot water over here, and we say that's like high voltage. So let's say it's 5 volts. Then there's a voltage drop across this ice cube resistor, right? So the water becomes less cold. So let's say it's 3 volts. And then you go past this other resistor over here, this blue one, and you have another voltage drop. So maybe it's, well, at this point it'd be 0 volts. And then that 0 volt water goes back into the battery and then comes out again. And since this resistor isn't connected to anything, it's not considered like an ice cube. It's maybe instead of ice cubes, I should think of it as like fridges. This fridge isn't connected to anything on the other terminal, so it's not turned on. So it can't cool down this water. So this water stays 3 volts. That's 3 volts. So with this example over here, we can imagine like this. Let's get a bigger paintbrush. So the hot water comes out of the battery like this. Okay. And it goes through a couple of fridges. So here's one fridge over here. Here's another fridge over here. Here's another fridge over here. Another fridge, and so on and so forth. This fridge over here is not plugged in on both sides, right? So it's not working. So we're just gonna leave it as white, like this, okay? Although white could be thought of as like snow, so maybe let's not make it white. Let's maybe make it black. It's turned off, right? Okay, so these are turned off. Okay, so the water moves down and goes past this resistor, and it cools down a little bit. So it goes from red, like this, to orange, because it cools down a little bit, and it spreads out like this. Spreads out, and we have this water coming down, and it turns orange, like so, and that spreads out like that, and then that water goes down like so, and then there's another ice cube here, so like that, or not ice cube, fridge, and that water cools down, so it goes from orange to yellow, and so on and so forth. Actually, let's finish it just for fun. So there's different paths here, right? These are all refrigerators. They're all plugged in. So what we'll do is we'll say now the water is turning kind of cool, so it goes through this path over here. So by the time it goes through this path, it turns into this color. So the yellow continues down like this, And of course, the water would also go down this way. So let's actually draw this as well. So it would go down like this. So it goes from red, passes over this fridge, turns orange, and that orange would go down like this. And anyway, I don't want to overcomplicate it because now it's, well, actually no, it's not being overcomplicated, very interestingly. Okay, so you have another fridge over here, like that, and the water turns from orange to yellow, like that. So they meet up, and the voltage is exactly the same over here, because the water mixes, right? So even if the voltage here was slightly higher than the voltage coming down from this section here, they would mix and they would come up with an average. So eventually, not eventually, like within fraction of a second, these would have the exact same voltage. So let's label these. So this 30 volts is the red water here, and I didn't do the math, but let's just assume that this is going to be 15 volts over here. So this is 15 volts. And then maybe down here, this yellow section would be like 10 volts, something like that. So anyways, the question was, right, like what is the voltage difference between point A and point B? Well, the voltage difference is VA minus VB, and we know that they're both at 15 volts. And so it's 0.